very much for giving us this talk. Francesca is now a fellow at the European Southern Observatory in Garching in Munich. A very short CV. She did her undergraduate studies in Bristol, I think, in the UK, and she got her master's in Barcelona. And then she did her PhD with Lia Thanasoula and Albert Bosma, and she received her degree in 2015 from the Laboratoire d'Astrophysique de Marseille. And then she worked as a postdoc at the Observatoire de Paris with Paola Di Matteo and Misha Haywood. And until her current position at ESO, she was a fellow at the Max Planck Institute of Astrophysics in Garching, working with Simon White and Volker Springel. Now, Francesca is very well known for her work on the dynamics of galaxies. Her research interests include galaxy formation and evolution, dynamics of barred galaxies, chemo-dynamics of Milky Way stellar populations, and body and hydrodynamical simulations, cosmological simulations. She also works with the connection between theory and observations. So she also works with Gaia and IFU multi-object spectroscopic surveys. And she's interested in the dark matter content of galaxies, studying the connection in general between detailed dynamical processes occurring in galaxies and the wider cosmological context always. I should also mention that Francesca is the founder and coordinator on behalf of Galileo Mobile of the award-winning project Columba Hypatia, Astronomy for Peace. This project is funded by the International Astronomical Union's Office of Astronomy for Development and the United Nations Peacekeeping Force in Cyprus and the MPA. So this is really important, I think, as well as the research. So thank you very much, Francesca. And without much ado, I would like to give you the floor. So Francesca is going to talk to us about barred galaxies in ΛCDM, clues on the formation, history, and dark matter content of Milky Way-type galaxies. So, Francesca.
Thank you very much, Despina. Thanks for the very nice introduction. It's a pleasure to be talking to you today. Thank you very much for the invitation. I really hope that at some point in the not too far future, I can actually visit you in person. Yes, let's see. The hope remains. So today, like Despina said, I'm going to tell you about barred galaxies in ΛCDM. And I'm going to focus in particular on what we can learn by studying cosmological simulations of galaxy formation and evolution, in particular focusing on two main questions. One is on how the Milky Way formed, and the other is on the dark matter content of barred galaxies. As Maria said, there's quite a broad range of expertise and also quite a lot of students possibly in the audience. I'm going to give first a very broad introduction and overview on barred galaxies in general and tell you why I think they're very interesting objects to study. And then I'm going to go into more detail on these two topics, on the formation of the Milky Way and on the pattern speed of bars and the dark matter content of barred galaxies. Okay, so starting very broadly, I'm sure you've all seen this kind of diagram before. So this is the Hubble tuning fork diagram in which Hubble classified galaxies according to their morphology. And on the left, you have the elliptical galaxies, and on the right, you have the spiral galaxies. And on the bottom here, you have the barred spiral galaxies, which is what I'll be telling you about today. Now, barred spiral galaxies, I think, are quite objectively the most beautiful galaxies, but they're also very interesting dynamical objects. They have this very elongated bar in the central region, which is made up of stars. And they're interesting. Also, one of the main reasons that they're interesting is that they're very bars are very frequent in galaxies. So over half of disk galaxies in the local universe have such bars. Now, apart from being quite frequent, they also do quite a lot of interesting things to the galaxy. So for example, bars can actually redistribute angular momentum from the inner disk to the outer disk and to the halo, and they can bring the galaxy into a lower energy configuration state, which is why bars are also very common phenomena in the universe. The other thing they do, which is interesting for galaxy formation evolution, is that bars can significantly affect the properties of their host galaxies. And they do this by basically redistributing stars and gas in the disk. So for example, bars can induce shocks in the gas that's in the disk. And these shocks are seen very often as these prominent dust lanes that you can see in barred galaxies. So this gas is forced to shock, and then it, of course, is forced to loses angular momentum, and therefore the gas funnels to the central regions of the galaxy along these dust lanes. When gas is pushed to the center, it accumulates in the central regions and can give rise to intense bursts of star formation, and it can form things such structures such as the nuclear disk or a nuclear ring, or which have also been called pseudobulges in the central regions of galaxies. And bars are also thought to be one of the main contributors to the fueling of the supermassive black hole at the central of spiral galaxies, especially at late times in the evolution of galaxies when mergers are a lot less frequent, and you need some other kind of mechanism that can torque the gas and make it funnel to the central regions. And bars can also redistribute stars both in the inner and the outer disk through resonances, and can lead to the formation of structures known as, for example, boxy peanut bulges in the central regions of galaxies. So I'm going to talk a little bit about resonant orbits. So here on the left, I'm showing you a simulation of a barred galaxy, and I'm going to show you three orbits in this simulation, which are resonant orbits. And these are seen in the inertial frame of reference. And now on the right, I'm showing you the same three orbits, but shown in a rotating frame of reference, rotating at the same speed as the bar. Now you see that these resonant orbits, essentially, they are trapped around a specific location in the galaxy. So for example, this orbit here is in the bar region as a bar supporting orbit. And these two orbits here are orbits that are trapped at co-rotation of the bar. So resonant orbits are those that fulfill the resonant condition in which the radial frequency is commensurate with the angular frequency of the orbit in a frame co-rotating with the bar. And what happens to these orbits, to these resonant orbits, is that they become very elongated. You can see this also in the inertial frame, but also in the rotating frame. And you can think of this a little bit as a forced oscillator. So basically the bar is acting on the orbits and changing the amplitude of the elongation of the orbits. And so it makes the orbits a lot more elongated. It changes the orbits from circular orbits to much more elongated orbits. Stable closed periodic orbits which is, for example, this orbit that you can see here in the XY plane, are really the backbone of stellar bars, and they trap around them other regular orbits, like the blue, which you can see in blue here. And here you can see how an orbit which is trapped around a closed periodic orbit kind of populates phase space in a barred galaxy. And you can see this here also in the surface of section diagram. And of course, you have many orbits of different energies within the bar, and these are what to really build up the bars in spiral galaxies. So now, as stars move around the galaxy, they also oscillate in the vertical direction, of course. And if they oscillate at a frequency which is commensurate also with the bar rotation, then these orbits will become resonant, as we said before. And these resonant orbits can get distorted out of the plane of the disk also. So you can think of this as, every time the orbit goes around the galaxy, it gets pushed upwards or downwards in the same direction. And so this forces the orbits to have these kinds of shapes, which look like essentially banana or pretzel-shaped orbits. And these are what give rise to the boxy peanut bulges that we see in disk galaxies, which are essentially just the bar seen edge-on. So here I'm showing you, I'm going to show you in an edge-on projection. So this, you can imagine the galaxy seen here edge-on. So this is the XZ plane. You can see here an orbit from a simulation, which is trapped by the bar into a 2-1 orbit. So an orbit that is part of the boxy peanut bulge. And you see that in the beginning, the orbit stays quite close to the plane of the galaxy. But as time progresses and the orbit gets trapped in resonance with the bar, you see that it gets pushed out of the plane of the galaxy onto these kinds of banana or pretzel-shaped orbits. And the cumulative effect of all these orbits is what gives rise to the boxy peanut shape that we see in many barred galaxies when we look at them edge-on. And so here I'm showing you, this is an n-body simulation now of a barred galaxy, of a spiral galaxy. You see it's axisymmetric in the beginning. So here you see the face-on projection of this galaxy. And on the bottom here, you see the edge-on projection. And I'm going to let it evolve, and it self-consistently forms a bar and spiral arms. And here I'm rotating the bar to be always along the x-axis. And that's because I want you to focus on the bottom panel here. And you see that sometime after the bar has formed, if I fast forward a bit, you'll see that there's an boxy peanut or X shape, which pops out after some time. So if I go back again, you can see that after some time, you have this very prominent X shape or boxy peanut shape in the galaxy. This is how these boxy peanut bulges form. Okay, so now we've had a little overview on barred galaxies. I'm going to dive into what all of this can tell us about the formation of the Milky Way's inner regions. So if we want to learn about the formation of the Milky Way or of galaxies in general, a really good place to look is in the inner regions of galaxies. And that's because the inner regions are, of course, the first to assemble. Now, in the inner regions of galaxies, we tend to find we can broadly distinguish these into two different categories. We tend to find so-called classical bulges, which are these dispersion-dominated spheroids, which are thought to form through rather violent processes such as mergers or clump migration at high redshift. And then on the other hand, we tend to find structures such as these so-called pseudobulges, so like the boxy peanut bulges that I've just mentioned, nuclear disks that are also thought to form from the bar pushing gas to the center, etc. And these structures have something in common, which is that they're thought to form through secular processes, so through disk instabilities or resonances. So these structures in the center have very different formation processes that also, of course, leave very different chemo-dynamical imprints on the stellar populations in the inner regions of galaxies. So by going and modeling the chemo-dynamical properties of the bulge, we can actually try and decipher the Milky Way's formation history. So first of all, what do we know about the properties of stellar populations of the Milky Way bulge? The first thing is that if we go and look at the morphology and the kinematics of the bulge of the Milky Way, what we see is that it has a so-called X or boxy or peanut shape. If you kind of squint a bit, so this is from the WISE survey, this is in the near infrared. And if you kind of squint a bit, you'll see that here in the center, there is an X shape. And this is, of course, thought to form through the buckling of the bar, like I just showed you. And in terms of kinematics, the stars in the bulge of the Milky Way exhibit so-called cylindrical rotation, which basically just means that the line of sight velocity of the stars is independent of height above the plane. So it's the same everywhere above the plane. And this is not what we'd expect in the scenario of a classical bulge. The reason we don't see this X shape as prominently as we see it in other galaxies in our Milky Way is related to the orientation of the bar with respect to the sun. And this is shown nicely by this video from the Athanasula. So this is a barred galaxy seen, let's say, from the outside. In the case of the Milky Way, of course, we're in the plane of the galaxy, and this is what the bar would look like if seen exactly edge on. But the bar in the Milky Way is actually thought to be have an angle of about 30 degrees with respect to our galactocentric line of sight. So the bar is essentially almost end on in the Milky Way. And this is why this X shape is not very prominent. Now, if we go and look at the chemistry of stars in the Milky Way bulge, what we see is that stars in the bulge have a very broad metallicity distribution function. And this is what you can see here. This is from the work of Zoccali et al. In 2008. This is showing you the metallicity of stars. And this is for a given field. This is for Badé's window, which is a field towards the bulge, which has low extinction. And you can see that stars have, a very wide range of metallicities from less than -1 to supersolar. And this very broad range of metallicities points to the coexistence of multiple stellar populations in the bulge. So there's been kind of a broad consensus from the community that these metal-rich populations are part of the same population as essentially the disk of the Milky Way, so that this population is what would participate very strongly in the boxy peanut shape, show cylindrical rotation, etc. However, there's been more debate, especially from the chemical and from the point of view of the ages of stars as well, but I won't go into that too much today, of what the origin of these stars with low metallicities in the Milky Way is. And there's two kind of main competing scenarios. The first scenario is that these metal poor stars in the bulge are part of a dispersion-dominated spheroid or a classical bulge. So essentially, in this scenario, the idea is that the Milky Way is a kind of composite bulge. So it has both a boxy peanut and a spheroid, a classical bulge. And the other scenario is that these metal poor populations in the bulge are actually just part of the thick disk that we see at the solar vicinity, but just continued into the inner regions of the galaxy. So of course, there's let's say, a spectrum between these two scenarios, between something that's dispersion dominated and something that has disk-like kinematics. It's not necessarily something that's completely bimodal or separate, but the difference here is not just semantic. So the difference here is that in this scenario, in which these metal poor populations are part of a classical bulge, what we're saying is that basically the formation mechanism of these populations is different from the formation mechanism of the thick disk, and that it's not enough to just have to just project the thick disk into the inner regions of the galaxy. We need to add some other kind of component to explain what we see in the bulge. Whereas in this scenario, what we're saying is that essentially, if we just continue what we see in the disk of the Milky Way into the central regions, we can explain everything we see, or almost everything we see, with those populations. So in this scenario, we're basically saying that the Milky Way bulge has essentially an almost entirely pure disk origin. So it's made up of the cold thin disk and the hot disk. Now, to investigate this scenario, what we did in Paris with Paola Di Matteo and Misha Haywood and other collaborators was to use tailored, isolated N-body simulations of a Milky Way-like galaxy in order to test this hypothesis and see if we can reproduce what we see in the bulge of the Milky Way just with these thin and thick disk. So what we did was to go and look at the disk of the Milky Way. So this is from the work of Bovi et al. In 2012, and here you can see radial scale length on the x-axis and the vertical scale length, vertical scale height on the y-axis. And this is showing you, so for different stellar populations, so for populations with different metallicities, which are color-coded according to metallicity here. And so what this tells us is basically that the metal poor populations in the disk of the Milky Way have a large scale height. So these are the so-called thick disk. And they also have a short radial scale length, so they're more centrally concentrated. Whereas the thin disk of the Milky Way, so these stars here, are more metal rich and have a larger radial scale length. So what we did was to say, okay, let's build an n-body model where we mimic this kind of behavior. So we built a discretized version of the disk of the Milky Way, where we have 3 disk components, which have scale lengths, scale heights, and disk kinematics that represent this discretized version of the Milky Way disk. And we assign to these populations metallicities and alpha abundances that correspond to these, the average values of these populations. And the masses of these populations were set according to a reconstructed star formation history of the Milky Way by Snaith et al. In 2014. And basically what you need to know is that these two, the intermediate and the very thick disk population, basically make up 50% of the mass of the disk. So these two populations are very massive, and the other half of the mass is in the thin disk. So we set up this n-body simulation. We have an axisymmetric disk, and we have a very stable initial conditions. So we use an algorithm by Rodionov and Athanasula, which produces initial conditions in equilibrium, and then we let it evolve self-consistently. It forms a bar, and after some time, it also forms a boxy peanut bulge. And then we go and observe the bulge of this model in the same way we observe the bulge of the Milky Way and see what we find there. So some of the things that we wanted to look at were the morphology, kinematics, and chemistry of the bulge in this model in comparison to the Milky Way. So I don't have much time, so I'm mostly going to talk about morphology today. So here I'm showing you what these kinds of models look like at the end of the simulation where the bar has formed, when we separate out again into what was originally the cold and what was originally the hot population, because in the simulation we can separate these out. So this is what the face-on distribution and the edge-on distribution of the cold population look like, and here for the hot population. And what you can see is that the cold population has a much more elongated bar and also a very prominent peanut morphology, more so compared to the hot population, which is a bit rounder, and the peanut is a lot less pronounced or less peanutty. And this effect, which was also discovered independently by de Baptiste in 2017, was labeled kinematic fractionation, where essentially the velocity dispersion of the population at birth will define how the population looks like at the end, after the bar forms, after the bar and the peanut form. And this has to do basically with the exchange of angular momentum between these two populations and the dark matter halo. So essentially what I'm showing you here is the angular momentum of the population as a function of these different populations and of the dark matter halo as a function of time. And what you see is that the thin disk loses a lot more angular momentum as compared to the thick disk, which is absorbed by the dark matter halo. And that's because this thin disk is colder, and so the stars are able to get trapped on more elongated orbits, and therefore they respond more strongly to the resonance, and they lose more angular momentum than the hotter population. So what's interesting here for the Milky Way is what happens when we go and look at this setup in a similar way to how we look at the bulge of the Milky Way. So what we did here was to take 3 different cuts at different heights above the plane, and to look at what the density distribution looks like for the stars in the cold and hot component. So this is what I'm showing you here. So this is along the bar major axis, which is kind of equivalent or similar to how we see the Milky Way bar bulge. And what you can see in blue here, so this is close to the plane, this is further away from the plane. And what you can see is that when we are close to the plane, the cold population and the hot population both have just one single peak in density, which corresponds just to the exponential, the peak in the exponential. Then when we move further away from the plane, what we see is that in the cold population, we see this double peak. And this corresponds to the 2 lobes of the peanut. So essentially we're cutting through the 2 sides of the peanut when we move along the bar. But we see that for the hot population or for the thick disk, we still only see a single peak. So the peanut isn't yet visible here. And if we move further away from the plane, then we see this double peak in the cold population even more prominently, and we also start to see it in the thick disk. Now this is interesting because if we go and look at stars in the bulge of the Milky Way, so these are now red clump giants, and this can be thought of as the magnitude can be thought of as a proxy to distance, because these are standard candles. And the gray line here is the metal-rich and colder population, and the blue line corresponds to the metal-poor and hotter population. And again, we see a similar trend. So for lines of sight that are close to the plane, we see a single peak in both of these populations. As we move further away from the plane, we start seeing a double peak in the metal-rich cold population, which we think corresponds to the peanut of the Milky Way, that we're crossing the two lobes of the peanut, but we don't see this in the metal-poor population. And as we move even further away from the plane, this double peak becomes much more visible in the metal-rich cold population, and it even perhaps starts to become visible in the metal-poor population, although there's debate about whether this feature really is robust, let's say. However, the important point to keep in mind is that these models are telling us that we don't need to see the double peak of the peanut in the metal-poor population at the same heights as the metal-rich population in order for the metal-poor population to be a thick disk. So the thick disk doesn't participate as strongly as the thin disk in the peanut. So we do see similar trends in morphology for the cold, hot, metal-rich, metal-poor populations in the Milky Way bulge. Now, I don't want to spend too much time on this because I also want to talk about the next point, which is about cosmological simulations. But I do have, so we also explored this for kinematics and the chemistry of the bulge using these tailored n-body simulations. And I have some slides at the end of the presentation. So if you have any questions on this, you can ask me at the end. But basically, what we found in this series of papers that we looked at was that these isolated tailored simulations of a thin and a thick disk can reproduce all the chemo-dynamical properties of the Milky Way that we went and looked at, including kinematics, chemistry, and morphology. And that this shows that the Milky Way bulge is compatible with having a mostly in situ or disk origin. Now, the question, of course, is, okay, but we think that bulges are mainly built up from mergers. So can we reproduce such a pure disk formation scenario in the ΛCDM cosmological context? Is this actually possible? So, excuse me. So to answer this question, we looked at the Arriga simulations, which are a suite of cosmological zoom-in magneto-hydrodynamical simulations, and that were presented in Grant et al. 2017. Here you can see the one of these models, one of these simulations. You can see the dark matter, the gas, and the stellar light projection as a function of time. These models have a comprehensive galaxy formation model, and they have masses in the range of the Milky Way, basically. And all of these simulations form essentially disk-dominated and star-forming galaxies by redshift 0 that reproduce a number of the observed scaling relations. And as you can see on the right here, at low redshift, already from redshift 1 and down, this galaxy has a very nice bar and spiral arms, and looks very much like a local barred spiral galaxy. So what we did was so there's 30 of these galaxies. So what we did was to go and look at all these 30 galaxies and pick those that actually have a boxy peanut bulge by redshift 0. And that's because we wanted to pick the galaxies that look the most like the Milky Way already. So we have this subsample of 5 Auriga galaxies that have a prominent boxy peanut bulge at redshift 0. And we did a number of things with these galaxies, but one of the things we went and looked at was the chemokinematic properties of these galaxies and compare these to the Milky Way. So what I'm showing you here now is actually for the Milky Way. So this is this is looking at the Argos survey so this is a survey looking at stars in the Bulge by Ellison et al. And what I'm showing you here is the line of sight velocity. The galactocentric velocity is a function of galactic longitude and the velocity dispersion here in the lower panel. And I'm separating into stars with 3 different metallicities. So metallicities above 0, from minus 0.5 to 0, and from -1 to minus 0.5. And what you can see is that in the Milky Way, all of these populations basically rotate quite similarly. So they're almost overlapping. Even though the metal pore population in the Milky Way bulge is hotter, as I've also said before. So this most metal pore population has hotter kinematics. So we went and observed the galaxies, our cosmological simulations, in a similar way as we observed the Milky Way, and we made similar kind of plots. So we rescale the simulation and we align the bar to 30 degrees as in the Milky Way and observe it in galactic coordinates. And so, sorry, what you see here, so these lines are now for one of these galaxies. This is for Auriga 18. And what you can see is that it doesn't do too badly in reproducing what we see in the Milky Way bulge, in the sense that the metal-rich and intermediate populations overlap in terms of velocity, and also the metal pore population is quite similar to the metal-rich population, even though the metal pore population has a higher velocity dispersion than the metal-rich populations. Now, if you go and look at another galaxy in our sample, this is Auriga 26, you see quite a different behavior. So the line here, you can see that the metal-rich and intermediate population almost overlap, but the metal pore population here rotates very slowly. And again, you reproduce a similar trend in the velocity dispersion, even though the metal pore population is even hotter here. And we did this for all 5 galaxies, and you can see that some of these, for example, 17 and 18, reproduce quite well what we see in the Milky Way in terms of the line of sight velocity and velocity dispersion, whereas others, like the one I already showed you, Auriga 26, does not reproduce very well what we see in the Milky Way. So the metal pore population is rotating very slowly. Now, if we go and look at these same galaxies and look at their morphology, again, separating into these 3 different metallicity bins, we see the same thing that we could also see in the idealized simulations, which is that, for example, if we focus on this galaxy here, we see that for the metal-rich population, we see the very prominent boxy peanut, whereas if we go to a more metal poor and hotter population, we see the peanut, but not as prominently. And if we go to an even more metal poor population, which is even hotter, we basically don't see the peanut at all within this region. And something else that that we can notice if we focus only on the metal poor populations is that if we look at the galaxies that have very slowly rotating metal poor populations, these are also the ones that have the most spheroidal-like distribution. Whereas the metal poor populations that rotate the galaxies that have metal pore populations that rotate fast, like 18 and 17, have a more flattened, thick disk-like morphology in this metal pore population. And now, of course, what we want to do is we want to relate all of this back to the formation history. So why, the question is why, what makes these galaxies different in their metal pore population? So this is what we're looking at here. So this is the star formation rate for the galaxies is given by the black line as a function of look-back time, and for the different populations, it's color-coded by different lines. And what I want you to notice here is on the top, I'm showing you, these lines show you when a merger happened in this galaxy. And these lines are color-coded by the stellar mass fraction of the merger. So lighter lines means that this was a very minor merger, and darker lines means that this was essentially a major merger. And what you can see is that if we look at, for example, these 2 galaxies that have the metal pore populations that are rotating very fast and which are similar to the Milky Way, what we see is that they have very few major mergers in the last 12 gigayears, especially in Auriga 17. You see there's almost no, there's almost no significant mergers in the last 12 gigayears. By contrast, if we look, for example, at this galaxy here, Auriga 26, which has a slowly rotating metal pore component, you see that there's two very significant mergers that happen at 9 and about 11 or 11 giga-years ago, respectively. And another quite significant merger that happens late in the galaxy's life. So what we see is that for Arriga bulges to have chemokinematic properties that are consistent with the Milky Way bulge, the last massive merger in the galaxy needs to take place at redshift above 3.5, or look back larger than 12 giga-years. However, we know that there's been a number of papers that have found a relatively recent merger, probably between 9 and 10 giga-years ago, called Gaia Enceladus, which is thought to have been quite a significant merger in the Milky Way. However, our models argue that this merger actually has to be less than a 1 to 20 merger. Otherwise, essentially what would happen is that this merger would destroy the nicely rotating metal pore component that we see in the bulge of the Milky Way. And this is compatible with some of the estimates from the literature from on the lower side. So there's various estimates in the literature, and some do suggest lower values. So the other thing we did was to go and look at now all of the galaxies in Auriga, all 30 galaxies, not just the 5 that have a boxy peanut. And what we did was to look at the difference in rotation between the metal-rich, the relative difference in rotation between the metal-rich and the metal pore component. So this is what I'm showing you here on the y-axis. And this value here is basically telling you, it tells you about how many mergers the galaxy has had. So it's a sum over all the mergers with stellar mass larger than 10 to the 7, I think. And it sums, this is the fraction, the stellar mass ratio of the merger over the redshift at which the merger happened, which basically tells you how important this merger was. So if it happened at small look back time, so recently, will have a bigger effect than if that merger happened at 12 giga-years ago. And if the stellar mass ratio was larger, it will also have a bigger effect. And what you see is that there's this kind of trend in which galaxies that have undergone more merging, more significant merging, have a larger difference between the metal poor and the metal rich population. So the metal poor populations rotate very slowly, whereas galaxies that have undergone very little merging have very similar metal rich and metal poor populations. And the Milky Way has this, the delta V in the Milky Way is somewhere down here. So what this tells us is that the Milky Way's formation history must have been very quiescent. So it's really probing the tail of the distribution of kind of possible merger histories in ΛCDM. But it is actually possible to have a galaxy that has had this kind of very quiescent merger history, and that therefore has a boxy peanut bulge that is essentially compatible with being a thin and a thick disk. And the other thing that we went and looked at was the fraction of in-situ stars in the bulge of these galaxies. And again, what we found was that in Auriga 17 and 18, which are the galaxies that look most like the Milky Way and that have had this very quiescent merger histories, the fraction of accreted stars in the bulge is less than 1%. So this is compatible with what we found also in the isolated simulations, that basically most of the bulge of the Milky Way is built by in-situ populations. Okay, and now I go to the last part of my talk, which is about the pattern speed of bars in cosmological simulations, and what this tells us about their dark matter content and how this relates to the so-called failed feedback problem. And I'll tell you more about that in a minute. So what is the connection between bars and dark matter? So there's been a number of theoretical studies that have shown that bars slow down basically due to dynamical friction when they're embedded in very concentrated and importantly live dark matter halos. So the idea is basically that, if you have a bar inside a galaxy, you have a given pattern speed. And if you look at an angular frequency plot, and your bar has a specific pattern speed denoted by omega p. There will be a radius in the galaxy, which is called the co-rotation radius, which is where stars on nearly circular orbits basically rotate with the same angular frequency as the bar. If the bar pattern speed decreases, you then get then the co-rotation radius will also increase. However, when bars slow down due to dynamical friction, the idea is that the bar length is not affected. So just, you can think of this bar as rotating, through like a bar rotating through some kind of sticky liquid. And of course, it can slow down because of the viscosity of this liquid, of this fluid, but the length of the bar doesn't change. So if you have a lot of dynamical friction acting on your bar, what happens is that the co-rotation radius will increase, but the bar radius will not increase. And so the ratio of co-rotation radius to bar radius will itself increase. Now this ratio, the ratio of the co-rotation radius to the bar radius, has been used to kind of determine whether bars are dynamically slow or fast. And in the literature, what's been used is that if this ratio is larger than 1.4, that means that the bar has slowed down a lot, and these are called slow bars. And if it's less than 1.4, then these are called fast bars, because there's a number of theoretical arguments that show that bars can be as fast, the co-rotation radius can be similar to the bar length. Now this is there's been a number of observations trying to determine the bar pattern speed. This is not trivial to do, but there have been a number of attempts in the literature. So now I'm showing you observations of this ratio. And you see that most bars tend to be kind of below this 1 to 1.4 line. So most bars are fast in the observed universe. Now, there hasn't been a lot of studies that have looked at the pattern speed of bars in ΛCDM cosmological simulations, but there have been 2 to date that look at a large enough sample. And these are using the Eagle and Illustris simulations in these papers that I cite here. And what they found, these studies, they found that in ΛCDM cosmological simulation, bars tend to slow down a lot compared to observations. Although it's kind of unclear what the reason for this is. Could it be low resolution? Could it be some grid physics? Or it could also just be an issue with, ΛCDM, that the halos are too concentrated. And this is, of course, kind of prompted these papers to suggest that fast bars might be, presenting a problem for ΛCDM and be incompatible with ΛCDM. So what we did was to go and look at the Arriga cosmological simulations, because we have a relatively large sample. We have 30 galaxies, and they're high resolution, and they form a lot of nice barred galaxies that satisfy a lot of the other properties of barred galaxies in terms of the observations. So what we did was to look at their pattern speed, and what we found is that the Arriga galaxies lie in this range here. So Arriga galaxies are actually have fast bars. And if we look at this ratio, the average value of this ratio R, you see that Arriga is compatible with observations, whereas Eagle and Illustris, of course, are not. So this suggests that fast bars are not incompatible with ΛCDM, because of course Arriga is done within the ΛCDM framework. But what is, the question is, of course, what is giving rise to these differences, these very big differences between Arriga and previous cosmological simulations? So one of the things that could be different is for example, could be the resolution, because Arriga is higher resolution than Eagle and Illustris. So to test this, what we did was to run some rerun our Arriga models, but with lower resolution. So these are the ones, these ones that have 5 next to them are the low resolution versions of the, let's say, the standard models that we used. And what we found is that, and these have resolutions that are a little bit higher, but comparable to Eagle and Illustris. So it's still a little bit better resolution, but quite similar to Eagle and Illustris. And what we found was that when we decreased the resolution of Arriga to be compatible to that of Eagle and Illustris, the bars are still fast. So it doesn't seem that resolution is the issue. Also, there have been other zoom simulations, so higher resolution simulations similar to Auriga, that also find that bars slow down. So resolution doesn't seem to be the main culprit here. So we looked at a couple of other things, but one of the things that we looked at was the baryon dominance of Auriga galaxies. So what I'm showing you here, this is the rotation curve for the Auriga barred galaxies. And what you see is that, so this blue line is this, for the stars is the average value, and red here is the dark matter. And you see therefore that the stellar component is dominant in Auriga galaxies in the inner regions. And this can be expressed with this value of the V star, which is the circular velocity due to the stellar component over the total circular velocity. And what I'm showing you here is this value for the Auriga galaxies in red, for the Eagle galaxies in purple, and for the illustrious galaxies in green. And what you see is that Auriga is more baryon dominated than the Eagle and illustrious galaxies everywhere, but also in the inner regions where the bar dominates. And this is important because we know that this baryon dominance is an important factor for whether or not, the ratio of baryons to dark matter is an important factor in slowing down bars. Now this has, the fact that Auriga is more baryon dominated than previous cosmological simulations like Eagle and Illustrious has some important ramifications. And this is that if we go and look at the stellar mass versus the halo mass of these galaxies, Auriga lies above Illustrious and Eagle, but also it lies above this dashed blue line, which is the value predicted by abundance matching. So basically, in abundance matching, what you do is you match, the stellar mass function of galaxies to the halo mass function in cosmological simulations, assuming a monotonic relation, and you get this kind of relation. So Eagle and Illustrious are both, Eagle is right on top of this relation, as one would expect to be kind of the norm for galaxies in ΛCDM. Illustrious is a bit higher, but you see Auriga is even higher and is more offset from this relation. Also, when we go and look at the efficiency with which with which gas is converted into stars, which is denoted by this F star here, and the blue line is again the relation from abundance matching. Purple and green are again Eagle and Illustrious, and Auriga is here. What we see is that Auriga galaxies are more efficient basically at converting gas into stars. And they're over 2 sigma offset from the abundance matching relation. Now this difference in all of this in the baryon dominance is essentially due to differences in the so-called subgrid recipes in these different simulations. So how they treat star formation, how they treat stellar and AGN feedback, etc. But something that's interesting is that what the dynamics of barred galaxies suggest is that massive spirals actually have to lie above the abundance matching relation. So galaxies need to be more baryon dominated than what's predicted by abundance matching in order to maintain fast rotating bars. And this is interesting because there's been also some studies recently by Lorenzo Posti and also by Marasco et al., who have also dynamically looked at this value here, F star, for spiral galaxies and compared it with the abundance matching relation. And what they found is that for massive spirals, they find that these massive spiral galaxies need to lie above the abundance matching relation. And they call this the failed feedback problem, that basically these massive spiral galaxies are very efficient at turning all of their gas into stars, more so than what is predicted by abundance matching. And so this kind of indicates that there is still, even though massive barred galaxies seem to, fast bars don't seem to be incompatible with ΛCDM. There is, because Auriga galaxies do have fast bars, and these are ΛCDM simulations, there does seem to be another problem, which is related to that these galaxies now need to be in tension with lambda CDM in terms of abundance matching. So it solves one problem, but it opens another problem. And whether or not this problem is really, bad, or if it's just an issue of adjusting the scatter of the abundance matching relation, it's still early days. So I think we need to look into this more. So then I'll leave you with some of my keep home messages. So in the first part of the talk, I told you about how both tailored n-body models and cosmological simulations suggest that the Milky Way bulge has basically an almost entirely in situ origin. So over 99% of the stars in the bulge are formed in situ. This has the implication that the Milky Way must have had quite an uncommonly quiescent merger history. So it's really probing the tail of the distribution of possible merger histories in lambda CDM. And also this places constraints on mergers in the last 12 giga-years that suggests that basically, also the famous Gaia Enceladus merger must be probably less than a 1 to 20 merger in order to reproduce what we see in the bulge of the Milky Way. And in the second part, I told you that fast spars seem to not be incompatible with lambda CDM in principle. It is actually possible to have fast spars in lambda CDM. So this big tension between, it's not as, is perhaps a bit overstated. However, the tension is that these massive spiral galaxies actually need to be more baryon dominated than what's predicted from abundance matching. And so this seems to suggest that massive spirals are overly efficient at converting gas into stars, and that in fact they need to be so for bars to remain fast and to match what we see in observations. And yeah, this has some interesting implications. So thank you very much for your attention. Oh, and one more thing. We also are having, we were supposed to have a conference this year, but because of COVID, it was postponed to next year. So if anyone is interested in bulges, bars, from high redshifts down to the local universe, please have a look at this conference that is going to happen now in November of this year. Okay, thank you very much.
Thank you very much, Francesca. Very, very interesting talk. A lot of progress has been made, I see. Are there any questions to Francesca?
I will have one.
Yes, please.
So thanks again, Edith, for this very, very nice talk. The question is about it was very, very thorough, very, very nice indeed. So about the abundance matching and the difference, you said it was kind of a selection made from before the deviation from the monster results of the abundance matching. So what was the trigger to deviate from it? What are the consequences for inflows? And just a quick comment on that the failed feedback is a bit, how could I say it? It's a bit misleading in the sense that the type of galaxies that it refers to, the papers you mentioned, are for massive spirals, whereas in most simulations of the past, it mostly referred to massive ellipticals. If you were to remove it, you would still have the problem of overforming massive ellipticals. So just about inflows and outflows, when you deviate from the abundance matching relations, what happens then? The budget.
Yes, thank you. Yeah, it's an important question. And sorry, I had to disappear from the screen. I had to plug in my charger. Yes, so about what happens in this range here, you're right that, so in the study, they're looking at massive spirals, whereas in this mass range, the idea is that you would kind of be dominated actually by ellipticals, right? I think this is what you mean.
Yeah, yes, if you were to remove you'd fall back to the initial problem of forming too many ellipticals, if you were to call it failed overall. So that was a bit of just a comment. That was just a comment. Mm-hmm. The question was what triggered the people who started deviating from the abundance matching? What was the trigger to go?
So this study is, it's just a dynamical study looking at the massive spirals. So it's not, this is just, kind of the result that comes out from dynamically modeling the massive spirals. I guess the idea is that in terms of what the inflows and outflows are doing, one could argue that at this mass range, because these galaxies are so massive, they're more efficient at retaining a lot of the gas, and therefore this makes them more efficient at converting that gas into stars. I don't know if that's a good enough explanation. And then the other question is, you know.
No, I don't think I expressed it perhaps correctly. In your simulations, what triggered, let alone the positive results, these are dynamical indeed from data. So how about in your simulations, what made people initially deviate from the abundance?
What made our simulations be more baryon?
Yes. Go back to the previous slide, please.
Yes.
The comparison. There, that's right. You said that was an assumption from initially made assumption. What made people do that assumption?
Yes. So indeed, so the Auriga galaxies are more lie above the abundance matching relation, but this was not done on purpose. So this was always seen as kind of a problem of Arriga, that we overshot a bit the stellar mass. So this is basically to do with the star formation and feedback recipes that were implemented. And these were simulations that were done after Illustris to correct some of the issues that Illustris had in terms of feedback, specifically the AGN feedback. So there were some differences that were implemented in Arriga, which uses the same code, a repo that also Illustris uses. And then we ran these simulations were ran, and they produced these galaxies that tended to be a little bit above the abundance matching relation. This wasn't done on purpose. It was just kind of happened by accident, and you know, was always explained as, well, okay, they're a little bit above, let's, you know, it's okay. But what we found when we went and actually looked at the bars then in these galaxies was that this happy coincidence or unhappy coincidence actually has some implications, which might be that, you know, these galaxies are first of all able to form a lot of bars, because the Arriga suite actually can form a lot of bars compared to some other cosmological simulations, and also that they stay fast. So it wasn't, it wasn't done on purpose. It was just something that came out of the star formation and feedback recipes.
Yeah, so you changed feedback, you had more massive galaxies, easier for the bars. But so last one, and then I let other people speak, sorry about that. It was very interesting for me. So what was the change in the feedback recipe that did that?
So, I mean, there were quite a few changes from Illustris, and there are quite a few differences from Eagle. So there we have the paper on archive. I list a few of these possible differences, but so for example, the difference between Arriga and Illustris is that in Illustris, the AGN feedback was very violent. There was this bubble feedback that basically blew out all of the gas, mostly in massive galaxies, but maybe also affected a little bit in the regime of Milky Way masses. Whereas in Arriga, the AGN feedback model was changed quite a lot and made much smoother in a sense. So the bubble feedback model was changed quite a lot. There are also some differences in how the stellar feedback was implemented. So in Arriga, at higher redshift, in Arriga, the stellar feedback is isotropic, whereas in Illustris it was bipolar, which might have some effects, especially at higher redshifts when galaxies are not really disks, and how the feedback acts on these galaxies, the stellar feedback. And in Eagle, also the feedback is much more bursty in general. Both the AGN and the stellar feedback in Eagle is very bursty. So in Arriga, it's a lot smoother. And one could maybe say even a bit weaker. So basically the feedback in Arriga is weaker than Illustris and Eagle. And for the details, maybe we can discuss more later.
Okay. Yeah, sure, that would be great. Yes, thanks a lot.
No worries.
I think I also have a naive question, Francesca, since we are waiting.
Sorry, I was trying to talk, and I had
okay.
my microphone muted. I'm sorry, and it kept asking. I'm sorry.
Okay.
So yeah. Any other questions? I'm sorry. Yeah.
I have a brief one. Probably it's very naive, but I was
then
wondering.
I'll ask mine. Yeah.
Yes. So I was wondering why the mergers of galaxies affect mostly the metal pool stars and not so much the metal rich? Yeah, it was not clear to me.
No, that's a really good question. So that has to do with the fact that also the when the different populations form. So if you look here, so the green is the metal poor population, the blue is the intermediate, and the red is the metal rich. So if you see, for example, the metal poor population is mostly forming at, even higher redshifts, and by, look back time 10, there's not much forming. So this population is essentially already in place at quite high redshifts. And so if you have a merger that happens, let's say at 9 gigayears ago, this population is already in place, whereas the intermediate population is still forming, and the metal-rich population is forming later on. So that can form from the gas that's brought in from that merger. But the metal-poor population is basically all the stars are already there, they're in place. So even if you have some kind of proto-disk, let's say, which might not be a thin disk, but might be a quite turbulent disk, if you have a merger that's massive enough to penetrate all the way into the central parts of the halo and get down to the bulge, it'll basically put all these metal poor populations on, dispersion dominated orbits. And so it'll mess up the disk-like kinematics and dynamics, which you need in order to get this kind of highly rotating population, basically.
Okay, thank you. And thank you also for the very nice talk.
Thank you.
Okay, sorry about the microphone earlier. So Francesca, I wanted to ask you the following. Is it a fair statement that when you have a prominent X-shaped bulge, then this is secular? Is that correct?
Yes. Yeah, I would say that that's a fair statement. But
yeah. So if one does, how often is it that we have X-shaped bulges? In the nearby universe. Do we have a statistical analysis to tell you how often that is?
Yes.
How often have galaxies that are not affected very much by major mergers?
Yeah, so I've forgotten the number, but there is a nice work by Lütike in 2001, Lütike et al. 2001. And I think the number is like 40% of edge-on galaxies are seen to have some kind of boxy or peanut-shaped bulge. So it's quite a high fraction, and it seems to be compatible with the fraction of barred galaxies that we see in face-on galaxies. Because of course the problem is, you either see the bar or you see the peanut if it's face-on or edge-on. So I think if I'm not remembering wrongly, I think it's about 40% in this paper that looked at edge-on galaxies. And then there's also been some studies by Irwin and De Battista who looked at inclined galaxies, but used a slightly different method to try, and basically they have a method where they claim they can see peanuts in inclined galaxies. And they also found quite a high fraction. So it seems to be comparable to the galaxies, to the amount of bars that we see in spirals, a bit lower, but comparable.
Yeah. So it's not that, So our galaxy is not that unique then. Not unique, but not so, so it's the norm, right? More or less.
Sure. The thing is that, of course, for example, in these galaxies that I've shown you here, in these 5 galaxies, they all have boxy peanuts. And you can, in this stellar light projection.
All Auriga ones. Okay.
All these 5 Auriga, yes. These 5 ones were chosen to have boxy peanuts. So you can still have a boxy peanut even when you have a larger ex-situ component. Although, so for example, here you have 10% of an ex-situ component, but this still has a boxy peanut. Now I have another plot, which I'm not sure I have in the presentation, but which is in the paper, which compares the ex-situ component in boxy peanut bulges and galaxies without a boxy peanut bulge but a bar, and in galaxies without a bar in Arriga, and this is increasing. So basically, the galaxies that have a boxy peanut bulge have, on average, the lowest ex-situ fraction, then the ones that don't have a boxy peanut but have a bar, and then the ones that don't have a bar. So yeah, this is, sorry, I don't have it here, but it's in the paper.
Yeah. Yeah, that's what I would have expected somehow. Yeah,
Mhm.
great. Thank you. Thanks very much. Thank you. Any other questions to Francesca? Okay. If there are no further questions, let's thank Francesca again very much for sharing these very important results with us. Thank you, Francesca.
Thank you very much for the invitation.
Great talk. Thank you.
Thank you.
Thank you.
Let's hope we